very, very happy to introduce Professor Andrieu-Brunsen to everybody. And it's a great pleasure to have you, Annette. Annette studied chemistry in Marburg in Germany, and she did her PhD in Mainz in Germany at the Max Planck Institute of Polymer Research. And she then moved to Buenos Aires in Argentina to do a postdoctoral research appointment. And in 2011, she moved back to Germany to start a junior professorship position at the Technische Universität in Darmstadt in Germany. And since 2018, she has been promoted as a full professor at the Technische Universität in Darmstadt in Germany. And Annette and we shared an office for a few years in Darmstadt, which was great. I still like to think back of those days. And she's a polymer chemist, and today she's going to talk to us about nanopores and ionic transport in these mesoporous materials. And Annette, the floor is all yours. We're very happy that you're here.
Yeah, thank you very much, Christina. It's a real pleasure, to be somehow at least virtually in the US tonight, and to take you on a journey, let's say, through nanopores. I was told that I have like 45 minutes or a little more, so I try to cover several topics in this time. But to get started, to give you a small feeling, because I assume not everybody of you is well in this nanopore or mesoporous business field or polymer field, I like to show these two images, which somehow represent for me at least the two extremes of what you could do with nanopores. So this is a reverse osmosis plant, where you see that in each of these boxes there are a lot of porous materials, and basically the aim is to that's the question for the audience. It's to basically purify water with these plants. And if you think about water management and future challenges in this area, the challenge and the usefulness of these porous materials is quite clear, I think. The other extreme of using a nanopore is demonstrated here as well, just an example from literature. This is graphene, but you could think of silicon nitride as well. And this is having a one single nanopore, well designed, and doing some DNA sequencing, as well a very specific community working deeply on this. But yeah, here you see the difference of having a lot of material, a lot of volume going through versus something very tiny, very specific, very precise. And we are somehow, I think, in between. If you think about this membrane and separation, this is usually how membranes are introduced or classified. You have something like ultrafiltration, nanofiltration, and so on. And this is mainly, not purely, but mainly based on size separation. This is relatively unselective. And if you want to be more selective, or if you again think about questions in the context of water management, you might be interested in more in the membrane molecule interaction. And this then relates to charge, to polarity, to wetability, ligand binding, in addition, of course, to the size, which still remains important, of course, but as well to process parameters. And this again is not that much our field. If we get interested in this, we do this in collaboration with engineers. And then, of course, concentration, temperature, pressure, flow, stability, and so on come into play. If now you have this technology component in mind, but you go a step back and think, how is nature actually doing this? So the bio-inspired approach. And from this perspective, I really like this image of the potassium channel, which was published 1998 in Science, and in which the color codes resemble different parts of this channel. So there is a size selectivity filter, but there are as well parts that have different charge, that have different wettability. And as these channels have a much better and more complex performance than any technological pore, this seems to be somehow important. And this is something that inspires us. And where we think, and this you will see throughout my talk, in some examples, how can you improve precision of functionalization of pores, and how does this correlate to the transport control? And then, of course, nature assembles this in very dynamic membranes, and everything gets very complex. And there you can think about architecture influences, composition control, and so on. Nevertheless, what nature does is designing transport selectively, direct transport, so from A to B or from B to A, but not both. To gate transport in time, to switch on and off. And usually you can achieve very high transport rates. And this then translated this biological approach or bio-inspired approach and this technological thoughts into what actually determines transport, and what do you have to influence, to play with, to understand in the nanopores beyond size. And this is charge. Of course, positive charges repel each other, negative charges repel each other, but positive and negative attract each other. So this is a principle that you can use to design transport. Wettability, I will go into this as well in some examples. So do you have fluid inhibition, yes or no? And how maybe even this in between influences transport. And then, of course, if you have very selective interaction, ligand binding, I will not go too much into detail into this in this talk. The material I will base my talk on is so-called mesoporous silica. I don't know if I can ask questions to the audience. Who knows what actually mesoporous means? This is quite important throughout this talk. Does anybody know what means mesoporous or mesopore?
The pore size between 2 and 50 nanometer.
Exactly. This is UPAC definition. So if I talk about mesopores, I mean pores between 2 and 50 nanometers. If I talk about micropores, it's below 2. If I talk about macropores, that's larger than 50 nanometers. And that's not intuitive for any discipline. So if I talk to other disciplines, they have completely different understanding of this, but this is UPAC definition. And if you hear the term nanopore, this is basically because I want to make clear it's a diameter in the nanometer range, but it's not a UPAC defined term, let's say. So we prepare these materials using either dip coating, quite common procedure in this nanopore sol gel chemistry community, or what we developed as well is gravure printing. So what you do in gravure printing, that you have a solution and a cylinder that goes through the solution and then deposits the solution on the substrate. And the advantage of this to dip coating, which is demonstrated here, so you basically immerse a substrate into a solution and you pull it out, is that the deposition is quite homogeneous. You can well control the thickness of these films, and it advantages if you want to deposit multi-layer films, because the contact time of the first layer with the solution for the second layer is not that long. You can see here that the film thicknesses can well be designed in both cases. And if you do this with a solution, and I will not explain the sol gel chemistry in detail, but basically you have a silica precursor molecule and you have templates, you have an assembly process, and afterwards you just calcinate the block copolymer template out, and this leaves the pores. And then this is what you get. So this is the macroscopic view of the dip coating, of the gravure printing. We could show that we can transfer these films, although they are not that stable if you have them in mind, like in hand like this. These are the TEM images, so you already see the nanopores. And these are the two working horses we mainly use. So we have pore sizes below 10 nanometers or something between 10 and 20 nanometers. Most of the examples I will show relate to this, this pore size. So with having this in mind, the rest of the talk will be structured in 3 parts. The first part will be on nanopore confinement, pKa value, and polymer functionalization. This is how we started into this field. And then I will go into the details about nanopore wetability and how this influences transport. And at the end, I'd like to go a little bit into detail on multiple functionalities and local functionalization of such pores. So what we do when we have this mesoporous material is, as we are polymer chemists, we like to functionalize them with polymers in a so-called grafting from approach. This means you try to bind covalently an initiator to these silane groups that you have at the pore wall surface. We use a lot this inhibitor-initiated polymerization, as this allows a certain control. It allows, as I will show you, reinitiation. But in contrast to, for example, ATRP, you do not need many other molecules to be present to keep the equilibrium of the polymerization or the control. We polymerized a lot of different polymers from perspective of transport. These are switterionic ones. I will show you the transport results on these. The PMAP was selected because it shows 2 different pKa values, and this is interesting in terms of confinement. PDMA-EMA is interesting as it's multi-responsive, so responsive to temperature and pH. And polymetallic is a nice working horse as it's a strong polyelectrolyte, has a permanent charge, and with this you can nicely control the charge density in these pores. If you do such a polymerization in a grafting from approach, of course you have to analyze what happens in your pores. And I didn't mention this, but the film thickness of our pore system is usually around, let's say, something between 50 nanometers and maybe 500 nanometers. The porosity is about 50, 40, 50, 30 volume percent. And then you can imagine that you do not have a lot of material. So the classical polymer analytics, degrafting, GPC, this is really, really difficult. And you cannot do this if you vary, let's say, the polymerization time for any sample, because you just need a lot of material. So what we usually do is that we measure ATR-IR. This is nice because you can normalize the spectra to the silica band, and then you can look, for example, at the CO vibrational band of your polymer. And here in this example for the PDMA-EMA, you see nicely that you can control the polymer amount in these films by polymerization time, for example. And another analysis method is using ellipsometry. Ellipsometry gives you the refractive index and the film thickness of such a thin film on a silicon wafer. And here you see plotted the refractive index and the pore-free volume, which you can extract from the refractive index, because if you polymerize, as indicated here, you fill the free pore space by polymer. Polymer has a certain refractive index, air has a certain refractive index, so you increase the refractive index. And from this, you can deduce the free pore volume or the pore filling degree from the refractive index values. And this corresponds to IR. You see that with polymerization time, you fill the pores basically. And you can reach relatively fairly high pore filling degrees. So if you know that you can do this, and you can do this with very different polymers, then of course, the question is, yeah, how does this then influence transport? And there are a lot of things to learn. So first, I'd like to introduce you with this PMAP example to how we measure this transport. As we have thin films, again, we have an electrode below this film. We use redox active test probe molecules. And as long as these redox active probe molecules can diffuse through this film and reach the electrode, you see a signal in the cyclic voltammogram. So this indicates transport is possible, and you can even get an information on the concentration of the redox active probe molecule. In this example, of course, it's obvious that you can just change the pH, so the polymer becomes negatively charged, and what you would expect intuitively is that the pores get electrostatically closed. This is because the pore size is in the range of the Debye screening length. I hope everybody somehow knows what this means. So basically, the distance that the molecules feel the electrostatic interaction is larger or in the same size range than the pore diameter. So this means that then the charged molecule arrives, and if it's negatively charged pore that it's getting in contact with, of course, it doesn't like to enter due to electrostatic repulsion. And this is then reflected in a decrease of the IP in the cyclic voltammogram as the molecule does not arrive at the electrode anymore. So this was, when we did this in 2012, this specific example, this was known, and we were interested what actually happens if you add calcium. And the intuitive hypothesis was that calcium, if you're a chemist, you know this, complexes phosphor groups. So you have two valent electrostatic interactions, and then the pore should get neutral. And this is actually what you see if you add calcium in low amounts. The pore opens again for the negatively charged probe molecule. So right now, I think this concept for a certain amount of polymer is demonstrated for almost every stimuli you can imagine. I recently read a paper, I think 2 years ago, that even magnetic stimuli have been investigated. So ions, pH, light, redox potentials. This works fairly well. So this opening and closing electrostatically by using responsive polymers. But if you use controlled polymerizations, and now you choose not the pH responsive polymer, but the strong polyelectrolyte, and this is the next step we did, you can control the charge density in the pores by the polymerization time or energy. And this is actually what you see in these cyclic voltammograms. So again, it's a negatively charged probe molecule that is electrostatically attracted by this polymer. And you see along the polymerization time that the IP increases, so the amount of ions in the pores increases. And what you basically do is that you go from a silanol regulated pore to over a neutral pore to a polymer regulated pore. And then with increasing charge density, increasing ions are present in that pore. To further understand the ion distribution along this pore size, and now keep in mind that this pore size is below 10 nanometers. We had a collaboration with a group of Igal Sleifer at Northwestern University, and they basically used their theory to first reproduce our cyclic voltammograms, but as well, and this is something that's just experimentally not possible, to get the ion distribution along the cross section of these pores. And here you have two cases. One is where you have basically one monomer per initiator. This is not really a polymer. And here you have 5, still an oligomer if you're a polymer chemist by education. And then what you see here is like in black, blue, and red, the polymer distribution along the pore diameter, pore cross section, the cations and the anions. And then you see two things. First, that the polymer or the chain length clearly influences the anion and cation distribution. And more interestingly here, you see from top to bottom the pH influence. And what you see here, if you have a certain chain length, that not only the polymer, but still the pore wall, because if you change the pH, you still have remaining silanol groups in addition to the polymer. And as well, these still influence the polymer, but as well the anion-cation distribution. And the anion distribution nicely follows the polymer distribution as well. So this shows you that even in this small dimensions, you have asymmetric distribution of ions along these pores. And this again is an interesting question, how this influences transport and how you can control this. If you then switch, and this is as well again interesting, you switch the polymer again, in this case, to this candidate, which can be zwitterionically or positively charged. So here you have a positive charge, and this is basically the same case what we had with polymetac before. And what you see here, independence of the polymer amount, is again this gradual behavior for the pore accessibility of a counter ion. And the positively charged molecule, this is basically quality control. If your pore system is intact, the transport is almost zero. So now the interesting point is what happens if you change to the zwitterionic state. What you would imagine very intuitively is that now, okay, that's neutral, right? You have a positive charge, you have a negative charge. It should be somehow similar, like with the example with the phosphate group with a calcium ion. This neutralizes and the pores open. But this is actually not what you see. You see first the polymer amount influence. But if you have a certain polymer amount, the pore is almost closed for the positively charged molecule, but it's as well closed for the negatively charged one. And this is not what you would expect intuitively. And this is a so-called bipolar pore. So what you see if you have zwitterionic polymers in these pores, that actually no counter ions independently of their charge like to enter these pores anymore. The next question then, of course, comes up, do this have to be a zwitterionic polymer? Or what actually happens if I now have a controlled polymerization in hand and I'm reinitiating the polymerization? So I polymerize 2-3 monomers of this positively charged polymer, and then another one that can be negatively charged or neutral. And we did this with the question how the chain architecture actually influences the transport. And what we see is that you go from an anion selective region to a cation selective region. And the interesting part here in between, in the middle, we do not see a bipolar pore. So at least for this system, we would conclude that the chain architecture has an influence and that it's not sufficient to just combine the two countercharged parts to get a bipolar pore. There has to be more, and it has to be combined maybe closer in one monomer. And if you, this is then in addition, just because we had this phosphate again in the copolymer, we checked the influence of calcium as well. And what you see is that calcium is blocking pre-concentration at basic pH and enhancing counter ion transport at acidic pH. And as well, this behavior is more complex than just the combination phosphate calcium. Of course, the calcium interacts with both partners, with both with everything that's present in the pore. Okay, so I gave you some examples on how you can polymerize on pores, which transport you actually observe. And then the question is, of course, how can you understand this? I already showed you the ion distribution. And I just like to get some break slide to introduce you in the possibilities that exist if you bring charges into these pores. So if you increase the charges or the charge density, of course, there's electrostatic repulsion. And in contrast to a solution or polymer solution, these charges cannot just increase their distance as they would like to do it if they would have space. So the question is, how can this be equilibrated? And then there are 3 possibilities. You can, of course, include counter ions. This is on the cost of reduction of their entropy. You can stretch the polymer chains to increase the distance. This is again on the cost of reduction of the conformational entropy. And you can shift the chemical equilibrium. This means at a certain situation, if you talk about pH, for example, let's say usually for this polymer it has a pKa value of 4. Now you have to bring in more energy to get the same charge situation that you would achieve at pK 4. So this pKa value would be shifted. And this is again an interesting topic in this nanopore community in terms of theoretical work, and a very few examples on experimental work. And we investigated this on the phosphate containing polymer by doing titration curves using cyclic voltammetry. So basically the same transport data that you saw before and just plotting the maximum of that curve against the pH value that you can adjust in the solution in the pore, and to get then an information of what happens inside the pore. And what you would expect actually is that you have a pKa value for MEP at 4.5 and 7.7. What we observe is that we see the first pKa value at 7.6, so strongly shifted. And the second pKa value for this system we could not detect anymore because at some point we have stability problems. And this is something that was somehow shown in literature in general for these nanoporous systems. And when we started doing these experiments, again, the group of Slifer, this was a nice coincidence, published exactly this system. So slightly different nanopore, slightly different diameter, slightly different molecular weight of the chain, but nevertheless this PMEP containing system. And what you see here is their data. And you see here in green, black, and red, the fraction of the neutral, once negatively and twice negatively charged PMEP side chain, and then of course extracted the pKa values. And in their system, under their conditions, they saw a shift to pH 6 of the first pKa value and the second pKa value around 10. And if you remember our data of the last slide, that we stopped around 10, we seem to have slightly higher shifts even, and then it is as well probably logic that we cannot detect the second pKa shift anymore if it's slightly above 10 even. So with this, I'd like to close the first part of my talk. So I showed you how to functionalize the polymers, how the type of polymer and the amount of polymer and the chain architecture influences the ionic pore accessibility, and how confinement influences the pKa values. So in the next part, I'd like to go from charge to wettability of these nanopores. And what we did to investigate the wettability, the first question was, can we gradually adjust the wettability of these films? And how does this then influence transport? So what we did is just gas phase deposition of this perfluorinated silane. What we observed is that we can tune the contact angle, so the macroscopic contact angle, from hydrophilic, so unfunctionalized, to hydrophobic and water exclusion. And then we used, again, these films to measure cyclic voltammetry, so pore accessibility. And what you see is that with increasing contact angle, looking at the positively charged probe molecule, for example, the pore accessibility is reduced and even completely blocked. And you see this for both probe molecules. And you see still a pH influence, which is logic, because even if you functionalize here, you still have silanol groups at the pore wall remain. So these are switched on if you go to basic pH. So the interesting curve here now, to our opinion, was the blue one, which at acidic pH does almost not show any pore accessibility for the positively charged probe molecule, but at basic pH it does. So there is a kind of switching on, which is wettability related. And this is this contact angle here around 70 degrees in our contact angle curve. And the question is how to explain this. And I will show you the data, but what we found out is that actually by doing this switching on of silanol groups at the pore wall, you probably get a condensated layer of water through which the transport occurs. And an indication for this is as well the shape of the CVs that you see. Whereas here below this contact angle, you have water-filled pores, and above this contact angle, you have water exclusion even at basic pH. Oops, and this is the data that supported our hypothesis here. What we did is water adsorption measurements, so changing relative humidity and measuring the refractive index with the ellipsometer. And what you see here in this blue curve is that at very high relative pressures, you still get water into the pores, whereas in the high contact angle, no water condenses anymore. This is then the data on the pore filling, which shows you that you have up to 13 volume% pore filling, but still this results cannot be explained by a fact that the pores would be fully filled. So there's still the majority of pore volume is still accessible. So what then happens if you deposit a droplet, and this is again very interesting on how fluid inhibition in these pores occurs actually, is that you see the formation of a so-called imbibition ring. So what is done here is you deposit a droplet, and what happens, I will show this in the video, is that this ring is forming, and now you can analyze the width of this ring and relate this to models of fluid imbibition in such materials. And there's a second thing happening, excuse me, that this fluid frontier oscillates, and you will see this in a kind of breathing movement in the video. So please just focus on this video, and what you see is that the droplet is deposited onto such a mesoporous film. So you see this imbibition ring, and you see now that maybe if you look closely, that it's slightly moving here at the front. So to learn something on the influence of this wetability on this imbibition ring, you can now analyze the width and the oscillation. And this was motivated by a work from an Argentinian group as well, who did this for different mesoporous structures. Yeah, this is the Argentinian group, and this is the group from France, actually. What you then get is just plotting the xt, so the width of the imbibition ring against the time. So what you saw in the video, basically 4 samples with different contact angle. And then you see this kind of curves that are very different in their initial phase, and then differently here in what we call the second stage as well. So the kinetics of fluid imbibition obviously depend on the wetability of these pores. And if you then zoom in, you can fit this with a model that was adapted from the Lucas-Washburn law. What you can conclude from this, that at the initial state, basically you have a kind of Lucas-Washburn imbibition, but then the second part cannot be explained by this, because after a certain time, evaporation becomes dominant. And as you have these nanoscale pores, what actually happens, and this is the explanation for the oscillation of the fluid front, is that you have constant evaporation and condensation just at the point of the fluid front. And this then leads to this oscillation. What we observe now, functionalized pores, is that here again, the fluid front often starts to move again. We are not yet sure what the exact explanation is, but we assume that this is a kind of activation at the imbibition front due to these condensation processes. But I cannot exactly state right now what exactly causes this effect. Yeah, this is again just the zooming into this oscillation, and you as well see that the that the amplitude of this oscillation decreases with increasing contact angle, and this again makes sense if you remember the water adsorption curves and the capillary condensation and dependence of the contact angle. So as well, this oscillation is wetability dependent. And now what you can do with this knowledge of wetability control and wetability transitions as well in these pores, because if you have now a state, if you remember, where no water imbibition occurs, and another state where water imbibition can be switched, and this was the interesting blue point at the very beginning I showed, you can think about, can we actually switch, not just by pH, but maybe as well by external stimuli, the imbibition, and at the same time droplet coalescence. And if you think about concepts like water production from humidity, such things might be interesting, and understanding of these things might be interesting. So what we did with the collaboration in this collaborative CRC project with the people from Dresden is depositing 2 drops on the surface close enough so they can merge. And this surface was functionalized with so-called spiropyranes. If you irradiate spiropyranes, they go into their merocyanine form. This is, of course, a reduced image because, of course, there are mesomeric forms of this. So only one is zwitterionically charged, but nevertheless, it's more polar. So you induce a light-induced polarity change. And if now you choose the initial contact angle in this state such that this polarity change is sufficient, although small in contact angle change, but sufficient to go via this fluid exclusion, fluid imbibition transition, then we were hoping to somehow get droplet coalescence and fluid imbibition at the same time. And this is what you see in the images here as a side view and as a top view. And on the next slide, I will just show you. I hope that works. show you a video on that. Oops. So what you would see is basically you have a tilted surface here. You would see that the light comes in, and then these droplets actually just merge and slide down the surface, not completely, but because the drop volume was just not large enough to get it sliding down by gravity, but merging down here basically. So this is then approach how, this functionalization, understanding of wetability in these pores and wetability transitions and polarity change upon irradiation can be used actually to get droplet coalescence induced and at the same time fluid imbibition. And to close this part of wetability control, I'd like just to draw your attention to the fact that if you have polymers in these pores, even ions can introduce wetability changes. That has a different reason, of course, that has to do with the polymer conformation, but that's as well pretty interesting if you think about separation, because in real separation, you will not just have your model ion present, but a mixture of ions. And what you see here is that, again, this polymetac polymer, and you just add different ions to the solution you are measuring contact angle with, or you immerse your substrate into these ionic solutions, and you see drastic contact angle changes up to hydrophobic pores. And this then again relates to the transport that you see. So depending on the ion present, now you see almost the ion exclusion of the probe molecule. And again, with the Slifer group, we did some theory without, in course of time, going too much into detail, but we saw that actually this is ligand binding dominated, and depending on the ligand binding constants, you can achieve these effects of ion exclusion in these systems. So the message here basically is, if you do real separations and you have polymers and polyelectrolytes in the system, be careful on which ions are present. So in the very last part of my talk, I'd like to go into a topic that I like a lot. I'm fascinated by this at the moment, and we are doing more and more work on this. And this is how to place multiple functionalities and how to precisely place them into pores. The motivation is that if you think about directed transport, you might have like two gates along such a pore that can orthogonally be gated. So open one, get the molecules in, close it, open the next one, and by this, for example, get directed transport into reality. The first project we did in this context was a collaboration with the group of Nikolaus Vogel at the University of Erlangen, and he did his postdoc with Joanna Eisenberg at Harvard, and is an expert on these opal monolayers and opal materials. And these are very, very interesting, though quite different to mesopores, much larger, but they are very interesting in terms of wetability control, because you can tune the pore opening angle, for example, and change the wetability. So our aspect in this was, our research question, can we place 3 different functions into each pore? And this is schematically depicted here. So we had these inverse opal monolayers, and the group of Nikolaus Vogel is able to just functionalize them with gold at the outer surface, with gold at the bottom of the pore. In addition, of course, now you have nanoscopic metal layers that are plasmonic, and you can think about using this plasmonic responses for sensing. This is what they did in the project. And then ask the question how to get 3 different functions. So one on the outer gold surface, one on the silane pore wall, silica pore wall, and one on the bottom gold layer. And we did this by combining orthogonal surface chemistry and wetability changes. So the first step was to use silane chemistry that then functionalized the silica pore wall in a pore wetted state. And then we added a ROM polymer that is quite hydrophobic. So again, that increases the de-wetting state of water in these pores. And the first step, then you can see already in electron microscopy that obviously there's polymer inside. The wetability, the contact angle increases drastically. So this as well indicates that functionalization worked out. And as well, infrared spectroscopy shows you that there is polymer in these pores. So the second step then was to discriminate the outer gold layer from the bottom gold layer. And this we did by using water as a solvent on a very hydrophobic pore. So the aim was to just functionalize the outer surface of the gold by using thiols, thiol deposition from water. The trick here is that actually you have to very well choose your thiol because you do not want functionalization via the gas phase. Then you can look at XPS data, for example, showing the sulfur band, but as well the nitrogen band of this charged thiol here. And you can, just analyze this by the IR spectra as well again. So then there's a third step. Now you change the wetability, you change the solvent to ethanol, and this then again wets the pore, and you again use thiol chemistry to functionalize the gold, first with an ATRP initiator and then performing the ATRP polymerization. And then as well, you see that you get these kind of polymer blobs in the under vacuum in the electron microscope. You see though it's small, you see the methacrylate band evolving in the IR spectra, which all indicates that there is a functionalization. And then, I didn't include the XPS data, which as well show all these functionalization steps, although it's quite difficult because here this is quite deep inside the pores. So the analytics is not that easy, but the XPS spectra as well show the different elements of the different functionalization steps. So this was one approach, combining inverse opal monolayers with orthogonal surface chemistry and different wetability steps to get 3 different functions into each pore. And then our project partners investigated this in terms of sensing and different plasmonics. And interestingly, what they thought, without going into detail, because that's not too much my expertise, that there is a plasmon band evolving that's quite sensitive actually to the silane region here, silica pore wall region here that was functionalized with the ROM polymer. And to finalize, just one more example on how you can locally functionalize pores that we were working on some years now to get as well the analytics done to show that probably this is really a nano-local functionalization, is using surface plasmons, not for sensing, which are they mostly used for, but as nanoscopic light source to initiate polymerization. The initial work on this was demonstrated on nanoparticles from the group of Zopera in Mulhouse in France. And they always used these nanoparticles and monitored with AFM the slight changes at the surface of the nanoparticles. And they could even show that the polymer, I think they cross-linked maybe a polymer, mainly the polymer, they could show that even the polymer amount reflects the plasmon field distribution. So what we did is incorporate this metal nanoparticles between different mesoporous layers. This is what you see here nicely in the TEM images and as well in the cross section. And then you have still one challenge, because these plasmons, doesn't matter if they are on planar surfaces or on particles, are usually in a wavelength range that is not compatible with everything that you know from classical light-induced polymerization. So you need a polymerization that matches this plasmon wavelength, which is usually, let's say, 400 nanometers or higher, and higher is more frequent. So a versatile mechanism again, and this was again taken from the work of Zopera, are dye-sensitized polymerizations. And they are not very much controlled from the perspective of a polymer chemist, but they are very versatile because you can perform them with the different monomers, and you have dyes of almost any wavelength in the visible range to go really even to 600, 700 nanometers for polymerization initiation. And this works actually quite well. And this is just to show you the results for the nanoparticle system. You see in TEM that there is a kind of corona evolving if you do this. You can, of course, analyze the plasmon band and estimate a kind of sensitivity from the UV-Vis spectra, but as well, this show increasing refractive index, which as well indicates that there is polymer formation. Oops. I skipped the other data. And I wanted to show a last slide with the infrared spectra. This is maybe the most important, where you see that if you do just the far field irradiation at the suitable intensity, there's no polymer formation. But if then you have the particles present due to the field enhancement, there is polymer formation. And now at the moment, we are as well driving this project in the direction of using not only this dye-sensitized polymerization, but using everything that comes from the field of visible polymerizations. And there are a lot of polymerizations now, even inhibitors or ATRP, that works under visible light, and to get this synchronized with this approach of nanoscopic plasmon-induced polymerization and polymer functionalization. And I think there's the first paper, this advanced functional materials paper, is out on this part of using controlled polymerizations in this technique. So with this, I hope I kept my time, and I'd like to conclude my talk. So I hope that I could take you on a journey from nanopore polymer functionalization and resulting transport using responsive polymers, and the influence of confinement effects that you have to take into account, demonstrated on the example of pKa shift, that besides electrostatic control, you can use wetability in these nanopores, which then again as well directly influences the transport, and not only the fluid inhibition as well, the ion transport, and then on concepts how to advance the polymer functionalization, for example, towards local control and having multiple functionalities with nanoscopic control, to go a little bit more towards the original image I showed you, which is a kind of inspiration of the potassium channel with its different zones of wetability, polarity, and charge density on the nanoscopic scale. With this, I'd like to acknowledge my group, of course. Due to COVID times, we should get a new picture, as some more people joined the group in the last 2 years, of course, and the funding agencies without which I would not have been able to perform all this research in the last years. And of course, thank you very much for your attention. Again, it's really a pleasure, and I'm really looking forward to your questions and the discussion.
Thank you, Annette. A very interesting talk. I think there is already one question in the chat by Bruno. Bruno, if you want to unmute yourself and maybe ask the question, and then I can also make the introduction, because Bruno is another one of our organizers for the materials seminar series. So let's see if Bruno is on. Yes, he is. There he is. Bruno, go ahead. You may ask the first question.
Oh, what a privilege. Annette, I really enjoyed your talk. A lot of things to meditate. We're working in interest in similar areas. And you just blew our minds with ideas, obviously.
Well, thanks.
One of the problems that we've been thinking about inhibition, and I think you touched upon it, this idea of condensation on the pores, right, in the walls of the pores, and I believe that was in the slide 28. But if you have a mixture, right, your droplet is a mixture of two things, right, and they are miscible. Right. So for, let's say, water to condensate, it has to separate from the mixture. And that means that the Higgs, Florey-Higgs criteria has to be overcome, right? You have to separate the molecules for that to happen. So only water will condensate. So how do you balance those two things, or how do we assess if that can happen?
I have to admit that we didn't touch mixtures yet in that collaborative project. And I would assume that you have to not strictly separate, but you have to take into account the evaporation rates that you have, because as well, let's assume ethanol water mixture, the ethanol would as well condensate. And then the question is, for each, and they would maybe even condensate in a mixture. So I'm aware of one publication, I think it was this French group, not 100% sure, so around Sanchez and Boissier, that actually did these things. And then you see that having a first liquid or a small layer, even a molecular layer, you can induce condensation. So it's not that easy, and I think you cannot just view this as two separated things linearly correlating. But I cannot tell you what happens because this we didn't touch yet.
Well, that was the hardest question I have in my repertoire, but it's so interesting your work. Thank you so much.
Yeah, thank you very much.
So I think there was another question, AMM Hazib. In case you want to ask your question yourself, please do so by unmuting, and then I don't have to read it.
Sure.
Oh, perfect. Thank you. Thank you so much.
Yes, thanks. It's a really excellent talk. By the way, I'm Professor Brunsen's PhD students. So we are working on kind of like the same project. So it was pretty fascinating to see like what's going on, and it's my privilege to learn a lot about it. One of the questions, actually, I think it's slide 28. It's from this one that I had, that when exactly that this Lucas-Washburn equation ceases to flow, because we saw that after a certain time, stage 1, when going to the stage 2, it ceases to flow, and why is that? Can you please explain? And the second part of the question is that we know that Lucas-Washburn equation is dependent not only the size of the pores, but also on the contact angle and the rheology of the fluids. So has there been any study done in your group or the group, you know, that to understand the confinement effect on rheology and how they influence the fluid transport or the fluid imbibition? Yeah.
So the first question is why this Lucas-Washburn applies and why it's steady state. Actually, I cannot answer you why. I can just tell you that you're right. There's the contact angle involved. There's a pore size involved, that from the literature I know, this Lucas-Washburn behavior is observed in case you exclude evaporation. So in case you have no evaporation, because of course this is not considered in Lucas-Washburn, you see this Lucas-Washburn-like behavior. But you have to be careful with one thing. This is of course a fit to that data. It's not a prediction. This rheology thing, we only used water in these things. So that's a Newtonian fluid. And you're right that you have this condensation layers and that there's literature on the adsorbed water that's quite strongly adsorbed. But so far I don't have information on the changing rheology of water in these pores, which for sure will happen directly at the surface, but I'm not sure that this is then determining for the fluid imbibition, because I think, yeah, maybe you can imagine this adsorbed layer as relatively constant. But I'm not a chemist looking at these flow phenomena.
I totally understand that. Yeah, I was like more interested, is there any study done beside water, like polymer solutions or something like that?
No, not yet. No. And polymers here, I mean, there are studies on polymer, not on the imbibition, well, I don't know, but I'm not aware of a study or not into it on the polymer imbibition in that. But what is certainly done a lot is polymer functionalization in terms of adsorption of polymer layers. And then, of course, this is much slower, but a polymer melt, let's say imbibition, I'm at least not aware of. And this, of course, would strongly depend on the molecular weight. And there's, of course, a sieving effect. So then I'm not sure if you can extrapolate what you see in water to these things, because there's, of course, strong interaction, and you would have to disentangle the polymer coil that it gets in if it really has high molecular weight, and at a certain point it would not go in anymore. Yeah, so this is more in the direction of the layer by layer functionalization of such pores, I would say. Yeah.
Understandable. Okay. Thank you.
And your second question, the contact angle. Yeah, I mean what the contact angle on the nanoscopic scale is, that's of course, I don't know. I don't have an answer to that. Yeah. So then it's as well, which contact angle are you talking about? I didn't show the hysteresis data here of the dynamic and static and receding contact angles, but they are of course in the publication. So this is always the macroscopic, and it's somewhere in between of this hysteresis, of course. But then, I mean, this is all the topic of this collaborative project here in Darmstadt. And I don't know if you're interested in these more microscopic contact angles. You might know the work of Butt at the Max Planck Institute in Mainz. So they are using high resolution microscopy techniques to then look into wetability and microscopic behavior of contact angles. For example, if you have advancing, receding, Cassie state, Wenceslates, and so on. I think that's a topic. Then again, completely different part. So yeah, what happens there at the nanoscale? Yeah.
Okay, Professor. Thank you.
Welcome.
Annette, I have a. Sorry, Christina. Can I ask a question?
Go ahead.
And this is probably a very elementary question, but how much control do you have on controlling the pore size distribution, if you may? I mean, using your standard.
Yeah. This depends if you. This is all determined basically by the sol gel chemistry on this process. So basically, the pore size distribution is quite homogeneous because you have this assembly process. So there's not a lot of hierarchy in the system if you take care on that. So you might have some micropores depending on the preparation. But this is the advantage of the system, that you can, if you think about real membranes, you have a very hierarchical system. And if you take these kind of model systems, you have a very narrow pore size distribution. And you can do like analytics such as infrared spectroscopy, but nevertheless get or deduce information on the nanopore level, because basically you assume all your pores are similar, plus minus half a nanometer or something. Yeah. Yeah. But this is on the sol gel chemistry, and then you have a flexibility, let's say, between micropores up to maybe 30, 35 nanometers. And if you want larger pores, then you have to go to different type of pores, let's say. So the sol gel chemistry with this assembly process, that's at least what I have in mind, goes to 30, 35 nanometers maybe.
Okay. I mean, my only question was, if you can control, if you can have a distribution or, bimodal distribution of pores, would it, I mean, then your transport, everything can be almost programmed, right? I mean, some of it, the nanopores handle, and some of it, the mesopores handle, and then you can control the transport. Is that something that you're looking into?
Yeah, that you do with with using different templates and layer-wise deposition, for example. And where we do this right now, but this is still more in its infancy, is in terms of getting these assembly processes in additive manufacturing. And then you have slightly different assembly processes, and then this is our hope that we can then do that. Yeah.
Okay, because I was actually going there. That's why.
Yeah. That would be if the paper can be published at some point. That would be very cool. Yeah.
Okay, that's awesome. Thanks, Annette.
Welcome.
Okay, I don't see a further question in the chat, so I'm going to hop in quickly with a question. And everybody, if you have another question, please make yourself known. So my question for now is, Annette, I was intrigued about the idea of using the plasmon effect of metal nanoparticles to induce polymerization. I hope I got that right.
Absolutely.
And your goal is to use that to locally determine where the polymerization happens, right?
Exactly. Yeah.
Maybe I missed it. How do you direct the nanoparticles exactly to where you want then the polymerization to happen? So how does that directional step work? And I may just have missed it.
Yeah, I mean, the question here is a little bit which plasmonic source you use. So the particles are one option. What we do here is basically this layer-wise deposition. So you have a mesoporous layer. You can tune the thickness of that layer. You can tune the porosity of that layer by using the template. Then we deposit the particles and deposit a second layer. So here you would have control in terms of the nanoparticle type you use and the thicknesses you adjust.
Mm-hmm. But do you assume coverage basically of the nanoparticles on your first layer?
Do you assume which coverage?
Yeah,
that's of course the point. Yeah, that's the point with these nanoparticles. So we can control this slightly. You do not want to get too close, at least not in our first study, because if you get too close, of course, then you have this plasmon coupling. This is what you did not want in the first study. Yeah, this is of course the question in this approach. If you want a fully closed layer at that point, how you would achieve that. That's maybe better by using a planar gold surface. You can use that as well, and then use basically plasmon resonance spectroscopy, but misuse it for polymerization, the setup. That's what we do as well. The problem there is we can show that this works. So you polymerize, that's nice. But the problem is to really analytically show and convince everybody that this stays nanolocal. This is the advantage of the particle, to just show, okay, you take all the data together and then it's very probable, yes, it's a nanolocal polymerization. So basically, in terms of which aim you would have with these nanolocal stuff, you would have to adjust a little bit how you go there. And we have two other techniques currently in development doing the same by basically misusing high resolution microscopy techniques.
Yeah, great, thank you. Are there more questions at this point? I don't hear any, and I don't see any in the chat. So thank you very much then again, Annette, for joining us. And we are going to free you into your Friday night.
That's excellent. My email post is still complete, so still some work to do, but maybe not tonight. Okay. Yeah, thank you very much. I enjoyed it really much, and I hope that at some point we can do this in presence. But still, then it was a pleasure to be with you in a virtually format.
Thanks for taking the time, Annette, and enjoy your weekend and your Friday night.
Yeah, you too the same. Bye.
Bye.
Bye. Bye, everybody.
Bye.